Devox UK. I'm very, very happy to be here. I'm ecstatic. This is my first time seeing people in forever, so that is wonderful. My name is Oleg Šelajev, and today we're going to talk about cloud-native Java microservices with GraalVM native image, which is, I feel this is a very interesting title because it compiles most of the buzzwords except blockchain that people are interested in. I work at the company called Atomic Jar, and I joined it just recently. And before that, I was a developer advocate for the GraalVM project at Oracle Labs at Oracle. So for a few years, I've been working with technology, trying to popularize that, solve all the problems that people encounter when they try to use it. And in this session, I would like to distill that into sort of the main areas of knowledge that you have to have when you want to use GraalVM native image specifically. Let's get started, right? What is GraalVM? GraalVM is a large project. It has a lot of moving parts. It is a high-performance virtual machine for running your applications in different languages. So it has support for a number of languages that you see on the slide, including JavaScript, Python, Ruby, R, WebAssembly. It can run LLVM bitcode through that, like a myriad other languages. It has support for all the JVM languages. So it's a really, really polyglot thing that can run it. One of the languages, or one of the groups of the languages that it can run is the JVM languages. GraalVM builds on the OpenJDK and builds on the hotspot virtual machine, providing a state-of-the-art, just-in-time compiler into that. So you can use GraalVM for your Java or JVM-based workloads just by using it normally. And by utilizing a better JIT, it can give you performance speed-up. And in the middle, loud, proud, and the most hyped aspect of GraalVM is the GraalVM native image technology, which allows you to take your Java application, take your JVM bytecode, feed it to the utility that will compile it ahead of time into a native binary native for a platform. This binary will not depend on the JVM. It will be standalone. It will be pre-compiled. So you can throw it into deployment environment, and you can start it. And because it doesn't depend on the JVM and everything is precompiled, it will have a very different performance profile from what you expect of your normal Java applications. So it will start fast. It will use less memory. And it will otherwise run the same way as your Java application runs. Those performance characteristics is what makes GraalVM native image really, really shine in the various cloud deployments, because that's what we want from our cloud applications. So this is a very quick introduction what GraalVM can do in general. And most of the session, we're going to concentrate on the native image technology and how you can use it, whether it works for applications, and what you should be mindful of. But just to be thorough, for Java developers, the most simple way to use GraalVM is just to download that and run your Java applications with it with a better JIT. So, and a better JIT gives you really good results, depending on the actual flavor of GraalVM that you're using. But it gives you better performance. It runs your applications faster. The ahead-of-time compilation also gives you better performance, but it's a little bit different flavor of performance. Because when we say performance, or we say, oh, my application is fast, what we mean, we usually mean different things. In the JVM world, in the Java world, in the Java ecosystem, we normally mean that the peak performance of our application is great. Right? My application is fast. That means that it starts normally, I apply load to it, it warms up, and eventually it becomes fast. And then it runs as fast as it can. And it can process as many requests per second or do as many operations per unit of time as we want it. This is one aspect. We call that throughput. And we would like to maximize it. Another aspect that we typically have in mind when we talk about performance is latency, which also has been optimized for, 27-ish years now in the Java ecosystem. And when we talk about latency and performance, we want to reduce the tail latency. So we want all requests, all business operations finish as soon as possible. Right? We don't want any users to wait. We don't want any of them to time out. We don't want any operation to stop and wait until something in the JVM happens. Both those characteristics are very well suited by running with a JIT. Because the just-in-time compiler would look at your application, will figure out which code runs, would figure out which data flows through your application, and then optimize it at runtime for the particular workloads and for particular code patterns that you have. This way, you can get, it has the best visibility into the pipeline of your application. It can optimize it the best, because maybe some code paths are never taken. Then it doesn't have to consider optimizing those. But it only can know that at runtime. That's why Java is actually pretty fast for those definitions of like what fast is. And that's why we are using that in all possible business contexts, in all possible systems across all companies and industries and projects. However, both of those are a little bit different when we talk about running our applications in the cloud. Specifically, if we want to chop our big system into smaller components, deploy them individually as microservices, and then scale them individually with the load, because that's what we want to do, what we want to achieve in the cloud. That means that we want our application to scale back and forth all the time. We normally don't want to have like preheated capacity of like JVMs running for ages, doing nothing, spending compute power, spending our cloud budget without actually serving our users. So we want to scale things up and down. That's how cloud operates. That's how languages and runtimes that are sort of cloud-friendly work. That's how the cloud deployments are supposed to be. For those, you need different performance characteristics. You want your applications to start fast, which is very reasonable. If you want your applications to not work almost up until the point when the users come, and then start serving business needs, it needs to start very fast and start doing business things as soon as possible. Like, you cannot allow your application to start for 2 minutes and then warm up for like 5 minutes before it gets to the peak throughput, because that's 7 minutes of people waiting if you didn't have the application handy running somewhere. You want your application to consume less memory. Not in a sense that you want to, you always want to consume less memory, and if you can pack your data in a more neat format or somehow use less memory for the actual data, that's very great. But what we're saying here is you want your overhead for running your application be as minimal as possible. If your application does nothing, it should be using like a few megabytes of RAM. It doesn't have to use like a lot, right? That allows you to pack your applications into smaller containers in the cloud and pack those smaller containers with very hard memory limits very densely into the memory. So if you can run one Java application and give it like 2 gigabytes of RAM, maybe you can run 8 smaller applications and give them like 256 megabytes of RAM. And then maybe those will scale better. That will give you more fine-grained power over tuning your applications and deploying your applications. And this is how clouds normally operate. So, and the third sort of thing that people, it's not directly related to performance, but this is what people very often mention when they talk about deploying to the cloud, is the size of the packaging. Nobody wants to create those giant Docker images and have your network pull, I don't know, gigabytes of your image just to serve a single application, because that also prevents you from easily scaling your deployment. If your Kubernetes cluster node goes down and you need to create a new node and replicate the environment there, it needs to pull the images, it needs to create everything. If those are actually like gigabytes of memory, then it will have to do that and spend time on that. So you want to package everything as neatly as possible into memory and run it in small containers, giving it just a bit of compute resources, and deploy it and scale automatically, and that would be an absolute dream. That's how those performance characteristics are something like other languages people usually use in the cloud. They all exhibit that. For example, Golang packs nicely into small applications, runs fast, starts fast. Might have different trade-offs of how it achieves that, but it usually works really, really well for the cloud. So this is what GraalVM native image can give you to a certain extent. And the graphs here are not to scale. Right? It's just an illustration where where you have better things or less better things, but it gives you a trade-off and it gives you an option how you would run your application. In GraalVM, you can run with widget, and you can run ahead of time compile package. So this is what it gives you. How do you get started with that? It's very simple. You have to download the package. GraalVM comes with the, it contains the download archive, contains the compatible JDK that you can get. The GraalVM team does regular releases. I think there are 4 releases a year, so it's like every 3 months. And you can download those, and you can run them. There are 2 flavors that you can get. There is a GraalVM community distribution, which is built from the open source components that are available for you on GitHub. It's all, most of that, right? All that technology, actually, which is really, really great. It's all written in Java, which is very good for many Java developers, me including, because I can open code in my IDE, stare at it, like pretend I understand what's going on there, and feel nice about myself. With code design languages, like in C++, I cannot even do that. So open source, you can observe that, you can try it. It is fully functional. It can do all the same things that the Enterprise Edition does, but the Enterprise Edition, that is a product by Oracle, paid product by Oracle, it does some things better. So it can run your application faster, it can run your native images faster, and it has some scalability and performance features there. Not affiliated with Oracle anymore, but if you want the absolute top technology from the GraalVM ecosystem that you can get your hands on, you should maybe consider thinking about that. But GraalVM Community Edition will be sufficient for all other deployments that I will show here, and many, many people are using that, so that would be absolutely normal to start just using that. How you download, how you get started, you download the thing, you unpack your distribution, it immediately has the normal Java utility that you want to use so you can run your Java application. And if you want to do the native image installation, you do need to run gu command to install the native image into your GraalVM distribution. It comes with like separate components that you can install into the main distribution. So for example, languages are distributed separately, so you don't have to, like when you download GraalVM, you don't immediately get Python or Ruby, because that would be counterintuitive, right? You kind of sort of download the JDK. So you can install them separately. You can install native image separately. And what it gives you when you run gu install native image, it will give you the ability to run native image utility and compile your applications. So, and now there is clear, separate life cycle of your applications that is happening. So normally, when we run Java applications, when I do Java minus jar my application jar, what happens is that Java process starts, and it starts doing things, and that is what we call a runtime. Everything that happens in that process is at runtime of my application, so it will do various things. It will load the classes at runtime. It will verify those classes. It will initialize those classes. It will prepare some class metadata that it has to store in memory. It will then start interpreting my classes, and it will start compiling my classes, creating the data structures for the compilation and whatnot. And all that will be at runtime. There is only one lifecycle stage when we run our Java applications, which is the runtime. And everything is done at runtime. There are smaller substages. So for example, if you run Java agents to instrument your bytecode, it also happens at runtime, but it also happens in a very specific time during the runtime, like in the beginning of the runtime. But there is just one runtime thing. It's counterintuitive, and it's really hard to understand and internalize. But when you run native image applications, there are 2 stages in the lifecycle. There is build time, and there is runtime. During the build time, we take our application, we take our jar file, or like a collection of class files in the class path, and the resources and configuration. And we instruct native image to look at all this and then compile it. And it produces us a binary or a log with mysterious errors, but normally binary. And to be honest, errors got much, much better in the last several years, so it's not that bad. But it's a separate process, and then eventually we can take that binary and we're going to start it. And that will be the runtime. Those two things are separated in time. Obviously, we first need to build our image, and then we need to run it. But they also can be separate geographically. It can be different machines. It can be different environments. You can build locally and deploy it somewhere. You can build it in a Docker container and then pull the image back somewhere. It can be an absolute different system. They're separated. There is no connection between those, which means certain things and certain trade-offs. So what happens during the build time? During the build time, what we do is the native image process, surprisingly, not many people know that. It's a Java application. It starts your JVM, and it starts loading classes, then it starts looking at the classes, and because the whole GraalVM is written in Java, it's also a Java process, so it runs it as a Java process, which you can inspect. You can put breakpoints in it if you wish. But what it does, it takes the bytecode of your application and configuration, and it first analyzes that. So you feed it your application classes. You feed it the classes of your libraries and dependencies that you have. You feed it the classes from the JDK standard library, runtime library. And you also feed it the classes from the Substrate VM, which is a project from Graal that provides you with the components of the runtime that your application expects and needs. Your application is written under the assumption that memory is infinite. You generate new objects. You create new objects all the time. You know that there is a garbage collection algorithm that somehow will reclaim memory and then make it sure that your application never runs out of memory to a limit. And when you compile it to the native image, it will still run the same way. So it doesn't magically transform your application, but it still compiles in the components of the runtime, such as garbage collector, such as how the runtime figures out the thread scheduling, and so on. So all those are equivalent, and they all are expressed as Java bytecode. So they all compiled at the same time. Then the compilation process is an iterative exploration of what our application actually does. So it starts loading the code, and it starts determining which classes and which members of the classes are actually accessed during or can be potentially accessed at the runtime of our application. So it follows the method calls, and it follows the object creation code, and it initializes certain classes if you want to. And it looks at what objects are created, what classes are initialized, and it compiles only those. It creates the full universe of the objects and the classes that will ever be executed during the lifetime of our application, and it only works with those. So it effectively prunes out everything that will not be run in our application, which is very useful because that first makes our packaging smaller. It makes our application faster. It makes it compile faster, but it also poses some challenges. This analysis is static. So it doesn't actually execute your code. It just looks at the code and determines what it needs to do. Then it takes all the code that it figured out that will be run. It compiles it using the optimizations. That takes a little bit of time. And then it writes the code out into the binary. This is one thing that it does. Another thing that it does, this process, it pre-initializes some data structures and some classes in your application. And this is very, very important. This is a source of like hundreds of errors that I've seen that people misunderstand what is happening. To be honest, it's very complex what is happening there. But this is the problem that it pre-initializes some data, and it serializes those objects into what we call image heap, and it writes them out. So what you can do during your build stage, you can prepare some data, and you can run that some of the Java code in the normal Java process with whatever the normal Java process can do for you. And then it will compile and serialize the data into the runtime. For example, you can initialize all the currencies or locals, or you want to initialize something else. Give me what's it different? Datetime converters. You might pre-initialize all of them if you want, and then save it into the process. So because of the analysis is static, that means that certain features of the language require additional configuration. Namely, there are a bunch of things that are happening dynamically at runtime. So things like reflection, things like GNI calls, things as generating proxies, things like using method handles for certain things like serialization, things like accessing resources because they are accessed through the, I don't know, class loader get resource instead of like calling a method with a dot. So the static analysis cannot figure out which resource you want to load because you might pass the name dynamically at runtime. Or the static analysis cannot figure all this out, which classes you want to access through reflection, because you also can generate the name of the classes that you want to access at runtime, or proxies. So the point is, the analysis cannot figure it out by itself. And what is the solution for that? As a developer, you have to provide configuration that tells the static analysis that you're going to use certain classes and access them through reflection. And the configuration is a very simple format JSON file that says, I'm going to access Java-lang string through reflection. Or I'm going to use a proxy on a certain interface, and we'll create a JDK proxy from that interface at runtime. Because the analysis cannot figure it out, but you as a developer can. So you provide this configuration. For example, we're going to use Java-lang string reflectively. What it means that during the analysis, it will see that, and it will treat Java-lang string, or whatever classes that you mentioned, as sort of the roots of the analysis tree as well. So it will know that that is a potential code that can be executed. So all code that goes through that code forward needs to be also considered for the analysis and for the inclusion into the final binary. Because if you cannot figure it out, it will not include those classes, it will prune them out, and then at runtime it will be a very unfortunate classes not found thing that will be unhappy. How do you provide that configuration? Because you can imagine there could be like very many classes that are accessed through reflection or proxies created. As a developer of the end user like application, you might not even know that there are certain things that are you doing things through reflection or dynamically somehow otherwise. Because who knows what their application stack is doing up to the lowest levels of Netty? Who thinks they know half of what that is doing? OK, nobody. Who thinks they know what their code is doing? Like what they wrote? Oh, a few optimists here. Very good. Yes, of course, we don't understand anything. That's in the job description. Like, if you cannot Google it effectively, then the information doesn't exist. So to help with this, there is a tooling that can help. Namely, there is a Java agent that you can run your application with and attach the Java agent to your normal Java process. And it will record all everything that is done through the things that needs to be configured. Right? It will record all the reflection usages, it will record the resources usages, and so on. You get the point. You run your application normally, and you execute the code path that you are interested in, and it will spit out the configuration for you. It will give you this giant JSON file that you then feed into the native image, and things magically work for the code path that you have been executing. Because it's a tracing agent, and it only can record things that it has seen in action. So the only reasonable, not the only, but the most reasonable place to run that agent is, of course, what? Your CI environment where you run your tests. Because if you've seen something pass in a test, that will also work in a native image. And it's very, very simple. You just literally run your application like that, and it will provide and will create a bunch of JSON files for you. And then you point native image to use those JSON files. So reflection and all those things are not a problem. What is a much larger problem is the class initialization, because it's less intuitive and more viral. Because reflection is when you use something through reflection and you know when it's an isolated thing. The class initialization is different. We have two parts of our build process, of our like runtime. We have the build time and we have the runtime. So the classes can be initialized at build time, and the classes can be initialized at runtime. And by default, the classes are initialized at runtime, because that is safer, because that is more reasonable. It's also less effective. It would be faster. It would be more efficient for the runtime of our application. The startup will be better and so on. If we could initialize classes at build time. Because everything that we do at runtime, specifically in the beginning of the runtime, eats into the precious milliseconds that our application is starting. And while it initializes something, it doesn't do the business things it needs to do. So if we could move everything to the build time, that would be splendid. And 3 years ago, that was the default. And we tried that. And it's very, very hard to make work with the actual code base that is in the wild in the Java ecosystem. That is just how it works. It will be very cool. There are a few problems with that. There are some objects. If you initialize classes, you initialize their static fields. If you initialize static fields, very often they are instantiated to be something. So when you instantiate to be something, you need to load those other classes. And before you can use them and create objects of them to store in the static fields, you need to initialize those classes as well. So naturally, if your classes have static fields, they will initialize more and more code, which might lead to a non-trivial chains of how classes are initialized. And you might not even know why exactly that happened. The same way that you don't know what classes and reflection usage and resource usage your framework does under the hood, the same way you will not guess easily or see easily the causality chains between the initialization of classes. So initializing things at build time is good and would be lovely, but it's really hard because it is viral. And then there are certain objects that cannot leave through the barrier here. You cannot, for example, open a file and store the open file somewhere during the build time and then successfully use that at runtime. That is just not possible because the runtime is a different machine. There might not be those files. There might not be files altogether. It might be like way in the future. You cannot, for example, initialize randoms. Well, you can, but it's really not advisable because if you initialize randoms and they are stored in the image heap, then at runtime they will give you the same sequences of numbers normally, because that's how pseudo-random generators work, right? You initialize them, you store them, and then you you get 4 all the time, which is usually not what you want from the random. But files handles threads, running threads. You cannot store a thread and make it restart there. If it's running and if it didn't stop, then the build process will yell at you, saying that I have a thread here, I don't know what to do with it. And you, as a developer, have to figure it out. Normally, there are solutions to that, but you get the point. There are certain objects that are no-go through the barrier here, through this separation. And the more classes you initialize, the more chances are that you will initialize and store one of those objects that can be transferred, and your build will fail. Normally, those are, for example, you initialize the async loggers for your loggers, and it will start an additional thread to flush the queues of messages somewhere at the shutdown. And that thread will prevent you from going between the runtime because that thread cannot be serialized. You might not even know that you're using async loggers or that it starts a background thread, but it will yell at you. So it's very important. It will yell at you when you start using that, most probably. But you might be you might be prepared for that now. Now, there is also, as with everything with native image, there are a ton of configuration options. There is a question here.
You mentioned a couple of points over here. So one of the points is when I build my any artifact, same artifact I deploy in various environments. Let's say development, UAT, production, and it uses environment variables, right? So will that also
Yes. So the question is, when you deploy the same artifact into different in different environments, it might also have the environment variables, depending on how you use those and how you read the configuration. If it reads the configuration at build time and bakes in that configuration into the binary, then, well, that configuration is already there. So you have to be sort of mindful about when you read the configuration files. Normally you don't want to do that in a static initializer because you never know when that would be run. But that is correct. So this is something that you definitely have to be mindful about. The solution to that is initialize everything at runtime. it doesn't affect performance that much. It still starts in milliseconds, and it's all good. There are configuration options that can give you the fine-grained control about when and how you initialize things. And you should just know that they exist. And another thing to know is most application frameworks that work with native image want to optimize themselves for better performance, for better startup, memory usage, and so on. So they want to initialize as much as at build time as possible. That means that there will be some classes that if you're using String or Quarkus or Micronaut or, I don't know, Picocli for command line applications or any other, there will be configuration options that say that some classes want to be initialized at build time. And the problem there is that sometimes that also includes your classes either by mistake or by accident, and then you as an end user, like end developer, will see the error message because you are compiling something. So talk to your application framework vendors as well. And there are knobs. There are documentation to the best of our abilities, what we created, that tries to help you through the process. And it's possible. Then the native image will work for a couple of minutes. It's a long process, but lately it got much, much faster using less memory. But it will take something like a few gigabytes of RAM and a few minutes to compile your small application, and more gigabytes of RAM and a little bit more minutes to compile a large application. It's not exactly a linear thing because there is the more classes it initializes and the more times it needs to do this iterative state analysis to figure out what is reachable, the longer the process will be. But if you can run the build on a powerful machine, like a few cores, like maybe 30 gigabytes of RAM, then it is much, much better than running it on a Raspberry Pi. Though you can run it on a Raspberry Pi as well. And it will print quite a bit of information. This is a sample that the GraalVM team wants to implement that gives you a lot of information about what goes into the build. Currently, it will do a little bit less, but all that information is somehow available, so you can debug that. You can look at under the hood what's happening. Remember, it's all Java. There is no secret sauce. As Java developers, you can definitely understand what's happening there and figure out using the tools that you're using for your application as well. And then you can report issues, and it will be all resolved. So you build your application. You get the binary file. What next? Next, you want to optimize that and maybe deploy it a little bit better to your cloud. You want to make native image use more efficient. There are a few tools that you might want to use for that. If you want to talk about the size of the application, there are two main aspects what you can do. There is a dashboard tool and some helpful reports that GraalVM Native Image Builder process prints out that can tell you which classes and which objects and which data contributes the most to your application size. This is very helpful to look at. It's not super helpful because the experience is not ideal there, but it is helpful, and you can identify some packages and some code that you actually don't want in your application, or maybe you don't need it in your application all the time. For example, if you look at the output there, not this particular one, but it just shows you which packages contribute the most. And you see that your XML configuration code takes too much space because it initializes the whole machinery to work with XML. But what you actually do is that you read one configuration file with it in the beginning of the application, and then your application never touches XML again. How many people work with XML all the time? Like read XML, write XML? 2. Very good. So you will probably need the XML machinery in your applications. The rest, probably not. But it will be there because some library reads a configuration file or is ready to read an XML configuration file. So it prepares with all the classes. And then you can see that, and maybe you can restructure your application or talk to maintainers of your libraries, and then they will not do the XML thing anymore. For example, I know that Hibernate did a little bit of work, and they optimized themselves for using with native image more efficiently. So this is how you reduce size. It also will reduce the compilation times because the less code it needs to analyze, the faster it is. So it's a win-win-win. It's an excellent thing. And if you want to optimize things even further, you might consider just compressing the executables. There are two utilities that I know that compress things very well. One is UPX, Universal Packager for Executables, I think. And it usually can compress your application to about 1/3 or 40% of the original size, because the output of this native image is quite a bit string heavy, so there is a lot of data in strings, and they compress very well. So you can get like 1/3 of the size. It will affect potentially the startup of your application a little bit, because it needs to unpack the things back in the beginning, but not dramatically. Usually they are very similar, or it's still much better than actually running the whole Java process there. And the second is the gz.exe, I think, file. I think that works for Linux only, but this is where we deploy our applications anyhow. So you might want to maybe see whether that works for you or not. But you can compress the things. And besides compressing just the binary, you want also to optimize your, because you're going to deploy it in a container. Who are we kidding? We take our applications with all the dynamic features that they offer. We package it in a Docker image that is immutable, that will never, ever load any classes except those that are in the Docker image already. And then we start a JVM that can load code from anywhere inside the Docker container created from that Docker image. And then we never load classes otherwise. So native image is very, very good, because we are already deploying our things as if they're immutable and not dynamically changeable. So we want to optimize the Docker containers as well. And what it means that you want to use probably Slim-based images as normal, but that means the Slim images here means the actually operating system Slim. You don't need Java there, because your image is standalone. You literally, your Docker file is 3 lines long. From base image, copy file, and entry point file. That's it. And you can run your application there. So another thing that you want to consider, maybe you don't need the operating system there at all. Your binary just links to libc dynamically, and then maybe you don't need the whole operating system. So you can use something called distroless Docker images, which will not contain the operating system. And they will be very small. I think the distroless native image that works with native image, distroless Docker image that works with native image, sorry, is something like 16 megabytes, which is kind of cool. And then you, for the small microservice, you add like 40 megabytes or 50 megabytes of the application on top. And under 100 meg, you get your fully functional Java application that is ready to be deployed. And if you are really into optimizing things and you want to have fine-grained control, what you can use also, you can compile your native image statically with the muscle C-based libc and all the libraries, and you will get one executable that is fully self-contained, and you throw it into the from scratch empty Docker image, like literally nothing else there, and you can run it. There are some trade-offs to that, because you do want like time zone data and maybe some other things in that image, but it will run in a from scratch Docker image. And it will be very small. I think the smallest, I had an example of a small Spring Boot application that does some sample calculation of numbers, like it was prime numbers or Fibonacci or something. And my Docker image for that was 19 megabytes. 19 megabytes Docker image of the Java application. That is mind-blowing. So you want to optimize that. You want to also optimize memory consumption. GraalVM native image offers you, by default, the GC algorithm that is used is a generational scavenger, which is similar to what the default GC was pre-Java 9, I think. In Java 9, we got the G1 GC, but before that, it was a parallel GC. And sort of, that's how you might think about the garbage collection in native image. So it has the young generation, and then it has survivor spaces, and it moves objects between those, and then eventually promotes them to the old generation, and then it garbage collects young generation separately, old generation separately. And it's a stop-the-world garbage collection. So you might experience some spikes in the latency. But given that it usually operates on smaller heaps, those pauses are not as dramatic as you would expect from a Java process that runs on like a multi-gigabyte heaps, which is not bad. And it also, you can configure the heap sizes and how much memory your application will consume. And you also can print the GC logs. And you can expect that. Yeah, and you can configure that. One thing that you want to know is that by default, that thing can have overhead over the maximal heap value that you provide, because I think at least until recently, it was copying when it garbage collected old generation, it copies that, right? So it's just a copying collector, so it doesn't compact in space. So when you have a lot of objects in the old generation and you need to garbage collect that, then it will take that data and copy again. So you potentially have quite a bit of overhead over the maximal heap, which is you might be mindful of. So if you make your maximal heap up to the memory limit of the Docker image, Docker container, then suddenly during GC you need more memory, and your orchestrator will kill a process, and you will be confused what's happening. You also can build in the memory usage settings at build time, which is very, very cool. If you are building, I don't know, command line tools, and you want your neat Java application not use more than like 50 or 100 megabytes of RAM, you can just say, like, this native image, by default, you have 64 megs of heap as maximal heap size. And then when it runs, that will be default. The user might override that, but like there is a default that is much, much lower than the unconstrained usage. Oh, this is also very important. If you just benchmark it in a powerful machine with a lot of memory, by default, native image doesn't constrain itself in the memory use. Just like a JVM, it looks at the memory available, and it thinks it's all for themselves. They're like, oh my god, I have 32 gigabytes of RAM on this machine. It's all for me. Excellent. So it will allocate and allocate and allocate and allocate and allocate until like 80% of your available RAM or something like this. So if you build native image on your laptop, which probably has plenty of RAM, and you run it and you apply load, you will see the memory spike. Doesn't mean that it's memory hungry. It just means you didn't constrain it. You can constrain it to lower values, and then it might as effectively run with like, I don't know, like 200 megabytes of RAM. It will do the GC more, so it will be a little bit slower, but it won't grow memory. Right, so memory configuration, very important. You must probably do that. Then, to addressing peak performance and latency, those things that were ahead of time compilation wasn't as efficient as running with a JIT. There are some offerings, and in the GraalVM Enterprise Edition, you can use the G1 GC, and you can use profile guide optimizations, which is where you sort of build an instrumented binary, and then you run it with the sample workload, and it will collect the profile, and then at the compilation stage, you can use that profile to run, to compile code better, to optimize your code for that profile. This is something the JIT does at runtime, and this is something that native image in the GraalVM Enterprise Edition can do at compile time. And then it leads you to wonderful results. So just recently, the GraalVM team, with the latest release, published some benchmarks. And on a number of benchmarks in the Java ecosystem, if you run them with PGO, with profile guide optimizations, and G1, then it gets very close to the performance of the warmed up OpenJDK with C2. So you don't even have to sacrifice peak performance there that much, which is very, very interesting. By default, the community edition doesn't get to the levels of the warmed up JIT, but there you have this dependency of the actual workload that you want to run and the deployment model. So for cloud workloads where you scale your things up and down anyhow, your JIT will never actually get to warm up because your application will just not see enough load for that. If it will see load, and if you can get through this slow warm up and startup, then running with a JIT is an absolute perfect way to run your Java applications. But if not, you might consider that. Right. So we sort of looked how to optimize the startup speed, how to memory footprint, packaging, peak throughput. Now, a little bit, I have a few minutes left, and I want to talk to you about how you can use GraalVM in your deployment pipeline. So you have this binary file. What do you do with it? Do you normal tools for tests. How do you run tests? How do you verify that your native image actually works the way you expect it to work? That's a very good question. Actually, tests are a very important question here. So how do you do that? Who has an idea? It's a Java application. How do you test Java applications? Who knows? Who tests their Java applications? Who throws it to the QA people and forgets about them? Committed and pushed means done. Come on, sometimes one person is honest. Very good. We run tests, of course. We run different types of tests. And since we have the runtime, it's very simple. Like we start our application and we start running code that verifies its behavior at runtime. So we use JUnit or Spock or other libraries for that. We use libraries like test containers to organize our integration tests. And in general, we just have sort of different types of tests. Some test implementation details as unit tests. Some test integration with different components, whether it works with databases and so on. And there are tools in the Java ecosystem that are excellent for those. There are unit testing libraries. There are integration testing libraries. There is also end-to-end integrated tests, which some people consider maybe not the best tool ever to be. Some people use effectively. So that's under the question whether you want it or not. But you definitely want unit tests, and you definitely want integration tests. So when we have the native image built, we have two stages. Actually, we have three stages there. Because before we start building the native image, we actually have the Java application that we can run. And it can run through the test pipelines just as well. So it can catch all your typos and all your logic mistakes in the code using the same tests as you always do. So first you verify that your Java application behaves as you expect, and then you start building native image. And then you want to run the same tests, and you will obviously want to run them during the runtime. Right? So you build the binary, and then you run that binary, and you want to execute some test logic there. Here what you have is the project called Native Build Tools. It provides you with build plugins for Maven and Gradle that help you build the native image, gather the configuration, and it also has the integration with the unit test frameworks with JUnit currently, but with unit test frameworks in general. What it allows it to do, it instruments your sort of life cycle of your build. And when you run tests normally, it will record which tests are run, and it will give you a stage where you can build the native image with the test code included, and it will then be able to run the tests that you run on the JVM mode inside the binary. So this way, you can run your application, you can build your tests, and then it will tell you, I discovered that many tests, and I built the native image here, and I run the test in the native image, and it all works splendidly, and you're happy, and you can deploy things. This is very, very excellent for libraries, because there you normally have your code coverage with unit tests. And if you have applications, it's a little bit less convenient, because very often you need integration tests. So for example, in a normal Java application microservice, you might have a test where you run your dependencies in a Docker container, and you run your application, and you apply, like, call API in your application, and then it will access the environment, and you verify that the application works with the database correctly, something like this. So in the native image, you can use absolutely the same thing, but a little bit more complex. So you take your application and you put it in Docker anyway, because you're going to deploy it in a Docker. That will be a small Docker file. That will be a small Docker image and Docker container that you run. And you can manage it the same way from your tests. So it will run inside Docker. And then you literally do the same thing. You have your application in a Docker, which is very small, and then you call API, and you verify that your integration tests work. So you just complicate the setup a little bit, but there are tools to make this efficient. And then if you talk about monitoring, this is the last thing, and I'm almost running out of time. The default tools for you will not work on native image, most probably Java agents-based approaches, because there is nothing to load the Java agent. So what you want to do, you want to bake in the metrics into your application when you build. So you use something like Micrometer, and you expose the metrics, and it's run. Or you can use the JFR recording, the JFR events, and then monitors those normally. And that support is built in. And of course, you can monitor your application resource consumption based on the environment around that. So you'd monitor your Docker consumption and so on. Time's up. So there are a number of projects that use various native image things. And I encourage you to look online for those. There are very many projects that support that. There are many frameworks that work with native image. So if you're starting new projects, you just might as well look into that because it's a very, very good thing. And yeah, there are challenges. It is much, much better situation than even several months before. Every 3 months, there are a ton of improvements. And yeah, I'm very happy that we are here in this with this technology now. And I would be very excited to hear what you build with GraalVM. Thank you.